Good afternoon to all the participants in post-lunch session. Now I welcome Dr. Ravi Kumar Mandava, sir. So we are honored to have you with us, sir, in 5 days faculty development program in Katihar Engineering College, organized by the Department of Computer Science. So sir has completed PhD in mechanical engineering in robotics from IIT Bhubaneswar. Sir has done Master of Engineering from Mechanical Engineering from Andhra University, Visakhapatnam. Sir has also done BTech in Mechanical Engineering from Acharya Nagarjuna University, Andhra Pradesh. Sir has research area is robotics, soft computing, manufacturing funding. Sir has project funded by, he is working on one ongoing project. Sir has published number of research papers in reputed journals and presented paper in conferences. So I welcome you, sir. Now you can start your session, sir.
Yeah, thank you. Thank you for a nice introduction about me, Dr. Kumar Yadav. 1 minute, I am going to share my presentation. Yeah.
Yes, sir, it is visible.
Yes, I think my presentation is visible.
Yes, sir, it is visible.
Yeah.
Okay, thank you.
Yeah, very good afternoon to everyone, all the participants, and those who are the this course are conducting the program event manager. Okay, I'm very good afternoon to, from my side. Actually, today I'm going to cover guide generation and design of PID controllers for the Biped robot. Maybe you have seen for the last 4 days. I think maybe you know about what is robot. Maybe you understood that, and maybe Dr. Vijay Bhaskar he may discuss about a little bit about related to Biped robot. Yeah, I'm going to cover completely the guide generation and how to design the PID controllers of the Biped robot. Generally, what will happen when we are going to discuss about robot means actually people they are thinking about the playing like a wheel robot and three-wheel robot and four-wheel robot. Generally, people will think like that. But actually, when they have started in 1921 by Karel Kepak, this term came robot. That time, his perception is it is a forced or slave laborer. That means whatever the work is going to be done by human being, that should be also possible by robot. When they have started in 1921, and then the first robot has invented in 1954, I think it is a Unimate robot. They have developed that is for manipulator in the sense it consists of a like how we have our human being arm, how we have like a shoulder joint, how we have a elbow joint, how we have a wrist joint. These things we have considered in the manipulator. That's why the manipulator it's looking like a human being arm. Then see, people they are using these manipulators for industrial purpose. They have started in industrial uses and for pick and place operation, for welding operation, for assembling operation. These are all the things people they are doing now. Then actually the research is going to start in how we need to do. See, one task is in industry. They are doing pick and place operation, assembly operation. Earlier in 1980s, that time actually 1960s, 1980s. These all the things done by human being. Then slowly they are going to convert as a like a robot. Okay, where the human being is there in the place of human being, they are going to keep in robot. But actually, see, one task what it is doing click and place operation. But slowly, what will happen? The people they are working on the suppose I want to move my material from one place to another place. Suppose I want to do some work in different places. Okay, I want to send my robot to in some place. How it is possible? Okay, it is not possible by manipulator. It is not possible by manipulator. Why? Because initially when they have developed the manipulator, it's a stationary position. It is a stationary robot. But what will happen when we want to move your robot from one place to another place? We want to provide some motion. How to provide the motion generally? See, there are two ways. One, we are going to provide the motion by wheels, or it may be by using legs. Okay. Then people have started to work on the wheel mobile robot. Okay, the wheel robot, wheel mobile robot or wheel robot. They are what they are doing. They are placing their manipulator on the top of the wheel robot, and they are sending from one place to another place. Suppose loading and unloading application. Suppose I want to pick the object from one place to, and I want to place in different place. Okay, in the different basket or something. Then I want to move in my robot from, in suppose you consider one room, I want to move from one corner to another corner. By using this wheel locomotion only it is possible. Later what will happen, the people they are facing the problem. Suppose if the surface, the structure of the surface, the floor surface is even, okay, then wheel locomotion is very good and it is more balanceable, and it is the work, the performance of work was good. But actually what would happen in all the cases, okay, wherever we are working, it may be industry or it may be outdoor environments, it is not possible to all the cases the surface should be in smooth, its surface should not should be in flat. Okay, but in some cases your surface should be maybe some uneven surfaces also. Okay, maybe some uneven surfaces. That means it may be in the surface there is some obstacles or some stairs, or it may be some ditch, or it may be whatever, there are some stones are there. That means your surface is not in flat. Okay, it is unstructured surface, it is unstructured surface. Okay, there are a lot of changes on your surface. Then you want to move, suppose you want to provide the locomotion to, okay, you want to provide the locomotion of your robot from one place to another place. Suppose when you are applying the locomotion to the wheel robot, what will happen, your robot will go there certain place, and wherever the stair will come, or wherever the stone will come, or wherever the obstacle will come, immediately it will stop. Or otherwise, okay, or otherwise there is a chance, if you can provide intelligent power, or if you can provide, okay, or you are controlling your robot in any remotely, you trying to operate to avoid that obstacle, it will may go in the next, it will take the turn and it will go, it may be left side or right side, it can turn. But the whatever the complete path, whatever the path we are providing the robot to move one place to another place, the complete path is made by some obstacle. Then how to do this type of challenging, okay, how to cross this type of challenge. Then actually the researchers they have started to work on legged robots. I think legged robots, generally we have seen the example of legged robots like a human being, like a dog, like those who are four-legged or two-legged robot. Then people are working on these legged robots. Why? Because see, the wheel robots, it is not possible to move in all the surfaces. Why? Because if the surface is unstructured environment, then you need to think about the legged robot. Why? Because the legged robot, it can make cross, it may cross, okay, it may cross the obstacle, or it may cross the ditch, it may cross the stone, whatever it may be, it may cross it, and it may walk on the stairs also. Then the people they are working on started to work on the legged robotics. See, in the legged robots, people have started the four-legged robots. Okay, then they have started in two-legged robot. See, why they are working on the two-legged robot? Suppose in the place of where the human being exactly working, I want to keep in the place of human being. I want to make it as a humanoid robot. I want to make it as a humanoid robot. I want to mimic the human structure exactly. But in that places, we are not possible to provide the four legs. We want to make the structure of the humanoid. Generally, human being we have only two legs. We have two legs and two arms. Okay, if you go for, if you think about the four-legged robot, if you think about the two-legged robot, see, the four-legged robot is the more balanceable than two-legged robot. Why? Because it's have four supporters. Okay, it have four supporting and contact surface of the ground, then it is more balanceable than compared with the two-legged robot. Then how to make this dynamic balance, how to make them more dynamically balanced, how? Okay, this is the one of the challenging work actually people are working in this area. And this while walking, see here there are two types. When you're standing making the balancing, it is easy. But when you're going to walk, when your robot is moving, that is dynamically moving. Okay, it means there are two conditions. One is static position, second is the dynamic position. When it is static position, no, you don't need to worry about. Okay, you just take care of your center of mass, then your robot may be balanceable. But when it is robot is walking, it is dynamic walking. Okay, then you need to take care of how much your robot is balanceable. Okay, this is the work I am going to discuss, how the robot when it is dynamically walking, how it is going to control, and how to design the PID control for each joint of the humanoid robot, And here what I'm going to discuss about, I think maybe you people know about it, the PID controller. We need to tune by we need to tune it, the PID controller. There are KP, KD, KI gains are there. Okay, here what I'm going to discuss, I'm going to discuss about how to tune the gains of the PID controller by using optimization algorithm. And another one is I'm going to discuss about the one of the neural network. Okay, artificial neural network.
Sorry to interrupt you, sir. I think slide is not.
No. Actually, I'm discussing
sir.
overall the view.
Okay,
Okay.
okay, sir.
I'll move. Okay.
Oh, some participants are writing that side. Okay, sir.
Okay. These are the things just my orally I am telling,
Oh,
but
okay.
there is no, these things are not there in any slide. Okay.
Thank
This is the thing I'm going to cover. And before going to the first, I think maybe people, some people may have what is biped robot. See, I'm going to discuss about the biped robot. See, it is the word, the biped word, it is coming from Latin word. The bi means two and ped means food. Here see, bipedal and humanoid robots are anthropomorphic robotic system, like our human structure, how the human structure is there. Okay, it is the anthropomorphic robotic system which try to mimic the human capabilities. Okay, suppose how human is walking. Okay, how I am going to walking. Okay, then how human is eating, how human is doing all the tasks. Okay, these type of tasks we are trying to mimic it. Okay, by using humanoid robot. Then see why we need to develop this type of humanoid robot. What is the necessity of the biped robot? See, suppose a biped robot, it is, see, you can see it is a two-legged walking machine that can perform walking like a human being. See, suppose if you are working in any industry, or it maybe if you want to keep, there is a person, security person in the any big shopping mall, or it may be or any hospital, there is a security person or there is a reception. Okay, there what will happen, the people, there is a receptionist is there, or it may be security people is there, they want to open the door and close the door. If you are facing any problem with the manpower, if you want to keep the robot there, humanoid robot, okay, that is the one of the tasks. That type of places we can use these humanoid robots. And see, biped robots are able to move in areas that are normally inaccessible to wheeled robots. Okay, earlier I have discussed. Okay, where it is, see, if it is a structured environments, it is the area, the total area is completely flat. Even the structured environment, even though it is a structured environment, the complete surface is the flat surface, then your robot is going to move. Okay, if you're leaving the wheel robot, then it can move perfectly. But if it is non-structured environment, okay, non-structured environment, or even though if any obstacles are there in the structured environment, okay, your robot is very difficult to move, the wheel robot. In that type of cases, we need to support of the biped robots. Suppose that's unstructured environment like such as stairs and areas littered with obstacles that make wheel locomotion is impossible. Where the wheel locomotion is impossible, in that type of places, we can involve this biped robot. Then see, coming to this biped robot, see, guide generation. See, simply I am telling, guide is nothing but, suppose when we are walking, okay, generally we will not observe when we are walking, that is called our guide. Okay, guide is nothing but one step, and when you are walking continue, that is called guide generation. Okay, that is called guide generation. See, guide generation is nothing but a sequence of steps. Okay, see, whatever we are doing, the number of steps we are walking, that is called the sequence of steps to move from one location to another. Suppose we are also walking, but we are not observing. That is called the technological term. Okay, the technical term is called a guide generation. A sequence of lift and release events of individual legs. Okay, generally what will happen? We are lift and we are when we are walking. Suppose when we are walking the continuous, suppose flat surface, we are moving the sequence order we are doing. Okay, or otherwise when you are walking on the continuously on the stage, we are moving sequentially. See, these guides divided into two main classes. One is periodic gait, second one is the non-periodic gait. What will happen when you're going to discuss about the periodic gait? See, suppose the same sequence of movement. Suppose you are walking on the flat surface. See, when you are walking on the flat surface, if you observe your guide cycle, there is no change in your guide cycle. The same structure of the guide cycle you are doing. Okay, but when you are walking on the non-structured environment, that means suppose there is a stair came suddenly. When you are walking on the flat surface, suddenly there is a stair came, or that suddenly there is a obstacle came. You are going to try to cross the obstacle, or you are going to try to walk on the stair. Then your guide cycle is changing. Okay, your guide, that means your walking system may change immediately. Okay, that is called non-periodic gait. That is called non-periodic gait or free gaits. Then see, you can see, observe here, I have shown here how the person is walking. Okay, see what will happen, always we are not touching the complete foot. When we are walking, always we are not touching the complete foot. Okay, see what will happen, this is a continuous walking or periodic gait. What will happen, we are trying to just touch and immediately we lift it. That time what will happen, sometimes it may touch. Okay, initially when we are going to touch, it will touch the heel position. Then when we are going to release the foot from the ground, we are going to touch the toe position. Okay, there are heel contact and toe contact. And then see, here in the walking cycle, generally when we are going to walking cycle, I have said the guide should be, there are two types. Then walking cycle is also two types. One is the single support phase, second one is the double support phase. Simply we can say that single support means one foot is attaching with the ground and second foot is the away from the ground. Okay, one foot is always touching the ground and second foot is the away from the ground. When we will see these type of cases, generally, see when we are going to cross something, when we are going to walk, okay, next step we are going to take, that time what will happen, whatever the one foot is touching with the ground, the second foot is in the air. That is called single support phase. See here, single support phase is one in which the robot takes forward stride and covers some distance only. We are going to take the forward stride and we are going to cover some distance. Okay, we are going to cover some distance. When we are, your foot is, the second foot is the air, that is called single support phase. But what is double support phase? See what will happen in the double support phase. See here, the two foot, the both the foot, okay, left and right, it is touching the ground. When it is touching the ground, but we are trying to lift the second, whatever the backward leg, when you are moving on the forward direction, the backward foot we are trying to lift. Okay, we are not lifted, we are trying to lift. That time our posture is changing. Okay, our position is changing, our body position is changing, our body center of mass is changing, okay, these all the things are changing. That is called double support phase. See here, double support phase is an instantaneous phase whose purpose is to exchange the leg support. We are going to exchange, we are going to try to exchange the leg support. That means we are going to try to cover some distance, okay, but not covering. Okay, in single support phase we are covering, but in the double support phase we are trying to exchange. Then you can see, when we are going to discuss about the bipedal walking system, I already said there are two types of bipedal walking system. One is the static walking, second one is the dynamic walking. See, static walking, what will happen? We are always considered based upon the center of mass. Okay, we will calculate how, I think we already know how to calculate the center of mass for one particular object. Okay, if we have already studied in maybe engineering mechanics how to calculate the center of mass for rectangular object, triangular object. Okay, it may be cylindrical bar. Okay, see here, with the static walking, the projection of center of mass of the robot is fall within the area of the foot support polygon. See here, there is a one more word, foot support polygon. We can see what is foot support polygon. See, you can observe my cursor. See here, this is the single support phase. One foot is attaching with the ground, the second foot is the air. That's why I am not showing here the second foot. And see the boundary of the foot is nothing but foot support polygon. That means when we are walking on the static walking, always whatever whatever your center of mass is there, if you calculate the center of mass of each and every component and you just sum it and make it the complete center of mass of your body, generally it will come on your, okay, body. Here position, it will come on the body. Okay, that will be the center of mass of the, where it is going to, the center of mass of the your robot, or it may be human being, generally where it is going to calculate. Okay, that it is where it is going to be fall down, sorry, where it is going to be fall down. It may be fall down, suppose in the single support phase, what will happen, it may be fall down within the foot support polygon. Or coming to the double support phase, support double support phase means what I said, both the foot are touching with the ground, but it is going to try to extend, try to just leave the that place. Okay, double support phase, this is the foot support polygon. This is the foot support polygon when it is in the double support phase. See what will happen here in the double support phase, your the center of mass, it may be any within this dotted line, okay, it may be this foot or it may be this foot or it may be in between. Then your robot is dynamically stable, Then here in the single support phase, your center of mass should be fall down within this polygon. Then only it is stable. Suppose if center of mass may be away from this, okay, away from this point, that foot support, okay, outside of the foot support, what will happen? Immediately will fall down. Immediately will fall down. See, static working is easier to implement, but it is usually unacceptably slow, with individual steps taking several steps. Okay, what will happen in the static walking? It is easy to implement. Why? Because we are going to calculate only the center of mass, but it is unacceptably slow. What will happen when you're going to discuss about the static walking? When you're going to do the static walking, what will happen? To cover some distance, it will take few minutes. It will take few hours like that. It will take more time than dynamic walking. It will take more time. Why? Because always it will stand one place, then we need to calculate the center of mass, and again it will move next place, then like that we need to do. And coming to the dynamic walking, see here the static walking, it works based upon the center of mass. Then we are going to discuss about the dynamic walking. Here dynamic walking, what will happen? The dynamic walking works based upon the zero moment point concept. It will work based upon the zero moment point concept. See, when we are going to discuss about what is zero moment point, see, zero moment point is nothing but it is defined as the point on the foot support interface. Okay, whatever the point, the zero moment point, we are going to define on the foot support interface. What is the foot support interface? This is the foot support. This is the foot support. That means foot support polygon. And see, this is the foot support here. See, and the foot support interface about which the moments generated by various limbs of the robot are equal to 0. Okay, where the ZMP point is acting, it is acting on the foot support interface. But how it is acting ZMP, how it is acting, how we are going to calculate the ZMP, the moments. Okay, we are going to calculate the moments. We are going to calculate the moments generated by various limbs of the robot. Okay, it's like human being, how we have 2 hands, 2 legs. Okay, how we have the robot, it also consists of, we have different parts like human being. We need to calculate the moments of the each limb of the robot, with the moment generated by various limbs of the robot are equal to 0. The amount of balance, okay, whatever the amount, okay, whatever the dynamic balance is it, the amount of balance is defined by the dynamic balance margin. Okay, now you can see, if I consider this part, see the thin line, this I am considering as a my lower limb of the leg, and this thick line, the back thick line, I think my cursor is visible. The black thick line, this you consider as a, okay, foot support length or foot support length, okay, or foot support interface. Okay, this is the black thick line. Here what will happen, your lower limb is connecting at the center of the foot support. Okay, from here to this end is the half of the foot support, and from here to here half of the foot support. Suppose if I am considering front side, or you can consider back side also. Okay, back side of the center of the foot. Okay, what will happen when you are going to walking on the forward motion, when you are going to try to walk on the forward motion, always your ZMP may be fall down in the front side, half of the center of the front side of the foot interface, it may be fall down. And see here what will happen after you calculate the moments. The ZMP is suppose is falling down here, exactly where the arrow is showing here, it is falling down here. Then see the distance between the point is acting on the foot support interface there too, and the distance between the point where it is acting, the ZMP point where it is acting, from there to the center of the foot, this distance. Okay, you see my cursor, this is the distance, this is called your ZMP distance. Then now what we are going to, why we are calculating this ZMP, we want to identify the dynamic balance margin. Why this dynamic balance margin is required? We want to calculate how much our robot is dynamically balanced. Okay, my robot is less dynamically balanced, my robot is more dynamically balanced when it is dynamic walking. See what will happen. See the distance between the point where it is acting from the center of the foot is called ZMP. Now see here what will happen, the remaining, okay, now you can see the remaining distance, whatever it may be there, okay, from here to here ZMP distance. Next, the remaining distance, whatever it is there, that is called dynamic balance margin. How much dynamic balance margin we can calculate it now here. Then what is the formula? You can see here. See that from here to here, suppose the total length is Fs. Then from here to here, Fs by 2 minus ZMP, this distance. Fs by 2 is the half of the foot support. The total distance is Fs. The half length is Fs by 2, half of the foot support interface. Then this distance, okay, Fs by 2 minus ZMP. Then your robot is how much dynamically balanced. We can calculate it. Then see, suppose my ZMP point is acting this position. Now I am showing my cursor. See, this point your ZMP is acting. Earlier it is acting here. Now it is acting this almost the edge of the foot surface, foot support interface. Okay. Now you can calculate your dynamic balance margin. It is see, very small. This from here to here. This is your dynamic balance margin. Then you can calculate. You can give the suggestion. My robot is less dynamically balanced when compared to earlier case. This is the way we are going to calculate the dynamic balance margin. Then only you can identify how much our robot is more dynamically balanced or less dynamically balanced. And for if you want to increase the dynamic balance margin, what we need to do? We are trying to do our ZMP point inside the. We are trying to do our ZMP point inside the foot support polygon. Trying to do. Okay, from the edge to trying to send the inside the foot support polygon. How it will come, how it will move, that depends on how your moment, that means how your robot is walking, how you are based on the motion you are going to create, and based on the you are going to calculate your moments. Okay, that means your body posture, how your body posture is, that you can correct also. Then see, coming to the applications, we already discussed in the earlier also. See, in the humanoid robot or biped robot, the people nowadays they are using in educational purpose. In the educational institutions, what they want to for teaching and laboratory facilities. Okay, there are two ways they are using in the educational facilities. One is for to teach the students. Second one is to keep this humanoid robot and for doing some lab experiments. Okay, the student can understand, okay, what are the different types of joints are there, how to calculate the dynamic balance margin, how to calculate the center of mass, okay, how to ZMP, how to calculate the ZMP, these things. There are two ways, one for teaching the students, second one is the to understand the laboratory, to understand the lab experiment. Then second one, they are going to use the malls and business centers. See here, malls and business centers. See, when you are entered into, suppose if you take any big mall, okay, big mall, there are number of shops are there inside the big mall. Okay, what are the inside? There are number of. Suppose I want to KFC is there, and I want to go for Big Bazaar. I want to go for Max. There are number of shops. Suppose I want to go exactly on Raymond showroom, but I don't know where it is in this big shopping mall. I am the new person to visit that shopping mall. I will go. There is a robot is standing there like a receptionist. I will go there. I will ask, where is the Raymond showroom, or where is the Max, where is the Big Bazaar? Then robot can guide you. You need to go take left. Robot can give the some suggestion. You need to go like this. Then immediately you will get the DB, that whatever it may be, Big Bazaar, you will get it like that. And also if you want to see what it will do, if you want, suppose opening, closing the doors, and safety. Suppose when we are going to discuss about this safety, okay, these robots, what will happen, suppose when you are going to do some operation is going on, like fire operation, something is there, any chemical operation, some chemical explode or fire explode, something will happen, that type of cases. If you are sending the human being, maybe he will also face the problem, he will also may die, he will also may get the damage. Okay, then if you send the humanoid robot, then it will give some try to protect ourselves and it will bring out, okay, for safety. And manufacturing applications, coming to the manufacturing, suppose if you see in the industries, even though there are the complete industry is the very smart. Okay, smart means you are working the complete industry by using the manipulators and all the non-conventional missions. Okay, all are non-conventional missions. That means everything is program type. Okay, but still you need manpower. Why manpower required? Sometimes what will happen, there are some of the things, maybe broken pieces we want to identify, or maybe we want to keep some things in the packing, while packing is coming or not, we want to check it. In that type of places, if you want to keep it, you can keep it the human being. And housework purpose, if you want to clean our houses, or heavy work also, if you want to do it as a human being, we cannot able to do, we can use this humanoid robot. Or suppose coming to the space application, suppose if you want to send, suppose actually recently the people, they went in US for space, okay, by using the space shuttle. See what will happen here, instead of sending, if you want to see something, if you don't know what will happen when you go there in the space, okay, we don't know whether the oxygen is available or not, or whether the things are available for food is available. If you want to send before sending the human being, you can send the robot also, and whatever the task is doing by human being, then the same task robot can also do there. Then you can put the nursing homes and hospitals and assistance for the people. What will happen, suppose in hospitals, if you want to, instead of suppose in like COVID, now COVID situation is there, very difficult to touch with the other person, and very difficult to people are fearing to talk with the other person. Even though our family member, they are fearing to talk. Why? Because if he is a COVID, and even the my mother, suppose mother and father or wife and husband also, they are very fear to interact with the people. Okay, if you go hospital, there are number of COVID patients, very difficult to interact with. Even though doctors also, they are also getting the COVID. In that type of places, what will happen? We are just leave the robot, and whatever the things they require, robot can take it, and the robot can provide the medicine, and it will collect from the medicine shop, and it will give the. And otherwise, one person we can supply these medicines, we need to give this room number 101, then robot can provide to room number 101 without touching. Okay, without touching any human being to human being, then robot will only touch like that. And also it will help to the elder people, those who are in homes. And also nowadays in this humanoid robot, they are helping the elder people, or they are helping some people, they have physically disabled people. Okay, in homes, actually most of the people, they are there in home. But when nowadays, actually both wife and husband both are doing work, okay, job. But who will take care of the elder people in home? Okay, this type of humanoid robot, it will take it. Okay, it may be grandma, grandpa, the robots will take care. How it will take care? Whatever the food they want require, just they will ask, then robot will go there, and it will bring the food or water, whatever the things, whatever the help they require. It can survive up to some assistance, some level. And coming to the hotels and restaurants, if you go for hotels and restaurants, what will happen here? Nowadays, actually, I have seen in Bengaluru, there is a robot. The robot is serve the food. Okay, it is servicing the food, and the same things nowadays, every places they are going to start. Why? Because one thing is that it is doing the same, the whatever the human being work it is doing. That means we are trying to reduce the manpower. The second thing is that people are interested to visit that hotel. Why? Because they want to see how the robot is working. That is, then they are getting more profit. That is the one of the technology people, the business people, they are using. This is the one of the application on hotels and restaurants. These are the different types of applications. Then coming to the biped robot, this is the one robot we have developed in my laboratory. This is the very small, like our kid has a 2 years kid, the height of the 2 years kid, like that. And the weight of this robot is 2 kg, and the height of this robot is 500 mm, that is 50 centimeter height. And the degrees of freedom of this robot is 12 degrees of freedom. The total degrees of freedom we have considered in 18 degrees of freedom, and 12 degrees of freedom is legs, and 6 degrees of freedom in hands. You can see here each leg consists of 6 degrees of freedom. See, when you are going to discuss about the hip joint, we are considered with 3 degrees of freedom, and knee joint 1 degrees of freedom, and ankle joint 2 degrees of freedom. Then total 6 degrees of freedom of each leg, and the total 2 legs 12 degrees of freedom. And when we are going to discuss about the hand, see here, hand, the shoulder joint consists of 2. Okay, it consists of 2. And similarly the elbow joint 1. Okay, 1 degrees of freedom. Then total 3 for each hand. Total 3 plus 3 6. The 6 degrees of freedom in hand. And now see the actuators. Okay, see here, one thing I am going to discuss actually. What will happen? As a human being, we have our own joints, but how the robot is working, how the robot is moving, how the robot is doing, performing some task, we need to provide some joints. What type of joints we need to provide? As a human being, we have own joints, but how the robot don't have own joints? We need to provide some artificial joints. That artificial joints is nothing but your actuators. We are going to provide the actuator. Okay, that actuators we have considered as a servo motor. See, we have considered 35 kg centimeter, depends upon the weight of the robot, and we have used for legs. And why? Because the total weight of the robot will be fall down on the legs only. That's why our whatever the motors we are servo motors, we are going to use the legs that should be capable to more torque. It will generate the more torque. That's why 35 kg centimeters. And when we are going to discuss, when we are going to attach the arms, we are going to use the 16 kg centimeter. And the power supply, we are supplied 7.4 volt lithium polymer battery. Initially we have supplied the direct power. Then later when we are going to test the real-time environment, we have used the battery power. Why? Because if we are when we are connecting the power supply, what will happen? The direct power, sometimes due to the wire also it may be faulted. Why? Because the height of the robot is very small, and the height and weight. Due to then sensors. Okay, we have used two different types of sensor. One is the accelerometer, second one is the gyroscope. And the communication, we have provided initially wired, then later wireless we have provided. Then controller, we have used Arduino Mega controller we have used. Then coming to the the parameters of various links of the biped robot. These are the various parameters we have calculated. The mass of each link from one joint to one joint. And the inertia, we have calculated which type of object we are taking as a link. Based on the object, we have calculated the inertia, the moment of inertia, and the length of the each link. Why? Because these all the things these all the things are helpful to calculate your zero moment point. Why? Because your mass, your inertia, your length should be required to calculate the zero moment point. Then see, this is the structure we have taken. This is the just skeleton diagram I am showing here. Here first, when the robot is walking on the flat surface, how the structure should be there. When the robot is walking on the stairs, and when the robot is walking on the descending the staircase, this is ascending the staircase. And when the robot is walking on the sloping surface, and here when the robot is walking on the descending the sloping surface. See what will happen here. See, I hear this is the structure of the robot. See, that is called sagittal plane, and this is called frontal plane. Okay, the sagittal plane means we will go for engineering drawing. Actually, we will discuss about the side view, front view, top view. Okay, the sagittal plane means, suppose when the robot is walking, suppose you are also as a human being is also walking. If someone is seeing from the side, our posture is like this. Someone is seeing from the side, our posture is like that. When you are walking on the flat surface, when we are walking on the stairs, our posture is like that. When we are walking on the descending the stairs, when we are walking on the sloping surface, our posture is like that. But when the person is standing in front of us when we are walking, what will happen? This is the frontal plane. Okay, the posture is like that. Okay, and also if you want to, you can try it. If you stand in front of the mirror and you can try it, the same type of posture we can get it. Then see what will happen. Any robotic problem, when we are going to develop the guide generation, or when we are going to calculate the torque, these are the things. Initially, suppose we are going to provide the motion of your robot. It is not a wheeled robot, it is a legged robot, like a manipulator. This is also one legged robot. If you want to provide any motion, you need to calculate you are calculating the motion. You are going to create the motion for your robot. That means your robot is moving. Okay, your left leg or right leg, any one leg, it is the position of the present position to the next position. It is moving the present position to next position. But what is the next position? What is the value of next position? That I need to calculate. That is called, suppose next position means, suppose x comma y. If it is a 2D plane, if it is a 3D plane, x comma y comma z. If it is a 2D plane, x comma y we can calculate. Okay, and if it is a 2D plane, we can calculate x comma y comma z. That how to calculate the position, what is the next position, how to identify. For that purpose, what we need to do, we need to calculate the forward kinematics. Yes, see, when we are going to calculate the forward kinematic, there is a systematic procedure. If you solve any robotic problem, like a manipulator, or it may be any legged robot, see here what will happen. First, we need to assign the coordinate frames for each joint of the robot. Okay, each joint of the robot. Here, see, we have considered there are two ways. One is the leg, and one is the arm. We have divided leg separately and arm separately. Initially, we have assigned the coordinate frames for each joint of the biped robot. Okay, similarly, we have assigned the coordinate frames each arm of the biped robot, and based on these coordinate frames, we have written the DH parameters. This is the one of the method. It is already standard method. You can see any textbook, it is available. Okay, that is the Dinavet-Hartenberg notation method. Okay, you can calculate. This is called AI is nothing but, for each joint, AI is nothing but your link length, alpha is nothing but twist angle, theta is nothing but joint angle, dA is nothing but your prismatic distance. See, what will happen always is not, see, when you're going to discuss about any robot, always it is not a revolute joints. Sometimes it may be prismatic joints also. Okay, prismatic joint means through and from motion, like reciprocal. Okay, linear motion. Prismatic joint means through and from motion. Linear motion will be also there, but sometimes maybe revolute motion is also there. That's why when it is theta, when it is going to revolutionary motion, then prismatic is 0. When it is prismatic something is there, then theta is 0. Then we need to calculate like this. Then the similar procedure we have adapted to harm also. Then we have calculated the DH notation. Then after calculating this DH table, we are going to keep these all the values into homogeneous transformation matrix. Based on the homogeneous transformation matrix, we can identify, we can determine what is the next position. We can determine the next, what is the next position. That is called forward kinematics. Forward kinematics is nothing but if we know the link length, if we know the joint angle. Suppose I know the link length, I know the joint angle, then I am going to determine the position and orientation of the next point. I am going to determine the position and orientation of the next point. Then coming to second one is the inverse kinematics. Here what will happen? I have calculated my position and orientation, that x, y, z. Okay, and I have calculated already theta x, theta y, theta z. I have calculated. Okay, then based on the position, what is the posture of my leg? What is the posture of my manipulator? That means what is the posture means what is the joint angle of my manipulator? What is the joint angle of my robot? Okay, we are going to determine the joint angles. That is called joint variables. See, the determination of all possible and feasible set of joint variables which would achieve the specific position and orientation of the manipulator. Suppose I want to reach this specified position and orientation. I want to reach the one position and orientation. What is the angle I require? That theta I need to calculate. That thetas I need to calculate. Here also we have calculated for this robot. We have calculated the joint angles. Where are the joint angles required? We have calculated by using inverse kinematics approach. And we have calculated joint angles when the robot is walking on the sagittal plane, that means side view, and when the robot is walking on the frontal plane. Okay, this is the way we need to calculate. This is the inverse kinematics approach. Then coming to see, now up to now we have discussed about the kinematics. Okay, this is the kinematics, forward and inverse kinematics is the kinematics concept. Then we will go for dynamics. See, coming to the dynamics here, what we are going to do, we are going to calculate the before going to the dynamics, we are going to calculate the dynamic balance margin. We are going to calculate the dynamic balance margin. See, earlier I have said how to calculate the zero moment point. I have shown one picture. There is a lower limb and there is a foot support interface, and the half of the foot support interface where the ZMP point is acting, from that point to the half of the center of the foot. The distance is called ZMP distance. The remaining distance is called your dynamic balance margin. See how we are going to calculate the ZMP. I said there is a moment generated by various limbs of the robot. How we are going to calculate it? This is the formula. This is the standard formula and developed by Vico Bretovic. Okay, Vico Bretovic. He is the father of ZMP. He is the father of ZMP. He has invented this problem. This is the formula, and this is the way we need to calculate. Here, see, I have written X ZMP and Y ZMP. What is X ZMP and what is Y ZMP? See, here my Z is common. My Z is common. See, in the both the diagrams, my Z is common. Why? Because one is related to sagittal plane, second one is related to frontal plane. Here my X, suppose if I consider this is Z, the Z is suppose height and X is length. X is the length. And here Y is my width. Y is my width of the foot, and Z is the height of the foot. Okay, here length and here width, and height is common. Height is common. And this is the way we are calculating the X ZMP in the sagittal plane, and this is the way we are going to calculate the Y ZMP in the frontal plane. Then what will happen? Now we have calculated the ZMP. We know what is the ZMP distance. We know the ZMP. Now we are going to identify how much your robot is dynamically balanced. How to identify? I already told you. This is the from here to here Fs by 2. So total length is Fs. From here to here half of the foot support interface. That is called Fs by 2 into cos alpha minus X ZMP. X ZMP, this is the mod of X ZMP, because if any negative value will come, we are trying to make it as a positive. Okay, and minus mod X ZMP. See why I have written cos alpha. See, this is the formula we have made for the complete. If any type of structure, if your robot is working on the flat surface, or it may be your robot is working on the stairs, it may be your robot is working on the slope surface, any type of structure, you can use the same formula to calculate the dynamic balance margin. How? See, the alpha is nothing but your slope of the surface, the angle of the surface. Alpha is nothing but angle. Suppose your robot is working on the flat surface, there is no slope in the surface. Okay, if it is flat, then your alpha is what? 0. Your alpha is 0, then cos 0 1. Then it will not create any harmful to your mathematics. Okay, your final solution. Then if your robot is working on the stairs, what will happen? Your robot is going to like flat. Okay, it will go one step, then it will go to next step. Then still now also what will happen? Your alpha is 0. Then see, when the robot is working on the slant surface, like slope surface, what will happen? There is a slope angle of the surface. There is a slope angle of the surface. It may be 2 degrees of the slope angle of the surface, or it may be 5 degrees, or it may be 8 degrees. That depends. That we are going to incorporate here. The cos, what is the alpha is nothing but the slope of the angle. Similarly, we have calculated the dynamic balance margin in x direction. We are going to calculate the dynamic balance margin in y direction. Then see, we have discussed about the kinematics and dynamic balance margin. Then we are going to discuss about the dynamics of the bipod robot. The main what is the purpose of the dynamics of the bipod robot? Because the reason is that when we are going to discuss about the dynamics, we already provide the actuators for the each joint of the robotic arm, or it may be bipod robot. Each joint there is a one actuator. Now we are going to calculate how much torque required for each joint of the robot. We are going to calculate, that is the thing. Okay, that torque we are going to calculate by using this dynamics of the, we are going to by using the dynamics concept. Okay, here what will happen when we are going to calculate these dynamics? We are going to use the Lagrange-Euler formulation. We are going to use the Lagrange-Euler formulation. I think maybe you all people know about the Lagrange-Euler formulation. It is a subtraction of, okay, it is a subtraction of the kinetic energy minus potential energy. Okay, one is the kinetic energy and potential energy. See, similarly here also we have calculated the dynamic balance, dynamics of the bipod robot. See, in this equation you can see this is the one of the Lagrange equation. It is developed by the kinetic energy and potential energy. And see here, this is the tau i. Tau i is nothing but the torque required. The torque required, and MIG is nothing but your moment of inertia matrix, and HIJK is nothing but, okay, see here, double dot is nothing but your angular acceleration, single dot is nothing but angular velocity, and HIJK is nothing but your Coriolis or centrifugal component. If it is a Coriolis, or it may be centrifugal component. GI is nothing but your gravity component. Okay, see, one is the moment of inertia component, second one is the centrifugal or Coriolis component, and third one is the gravity component. See here what will happen. The tau I indicates the force applied at joint A, or it may be torque required at joint A. And see, when we are going to calculate this inertia term, okay, the inertia matrix MIJ, we are going to use this procedure. And when we are going to calculate the centrifugal or Coriolis term, we are going to use this procedure. Then we are going to discuss about the gravity. We are going to use this procedure. See here what will happen. We need to do some matrix multiplication and trace. Only differentiation, multiplication, and trace we need to do. Then only there is no big task when we are going to discuss about the dynamics. Only you need to do the matrix multiplication. See, once we have calculated the dynamics, okay, now you know what is the, we are going to calculate what is the torque required. Okay, we are going to what is the torque required for each joint of the bipod robot. Now see what we have discussed up to now. We have discussed about the kinematics and the dynamics of the only bipod robot. Okay, how to generate the Gait. Okay, now we know how to generate the Gait. How we are going to generate the Gait? By using your forward and inverse kinematics. How we are going to by using your forward and inverse kinematics? Your forward kinematics will help to what is the next position? What is the next position? Then inverse kinematics, what it will do based upon the next position, what my joint angles, what my left leg of the joint angles, and what my right leg of the joint angles, it will calculate by using inverse kinematics. Now your robot is moving from one position to another position. That is called Gait is generating. Now Gait is generating. Your robot is moving from one position to another position. Then you are generating the Gait. Okay. Then you are going to calculate the how much torque is required to move from one location to another position, one location to another location, how much torque required. That also we are going to calculate it by using dynamics of the biped robot. Now my question is that I want to control my biped robot. How to control? I want to control my biped robot. Okay, I want to increase my dynamic balance margin. How to control? I want to play with my joint actuators. I want to play with my joint actuator. Suppose I am giving the input to the joint actuator, whatever the joint actuator. Suppose I want to move my initial position, my initial position of the joint one. Suppose you take any one joint, my initial position of the joint one is initially it is 30 degrees. Now I want to move my joint position. Okay, I want to move joint position from 30 to 45 degrees. It will move exactly 45, or it may move exactly 44, or it may be exactly 46. Okay, that we need to check it. Then when we are going to reach exactly 45, then only your robot is controlling, more controllable, more dynamically balanceable. Okay, that means your ZMP point is matching exactly inside this polygon only. Suppose if you want to reach your joint exactly 45, but your joint is reaching exactly 43, then what will happen? There is some error. There is some error. Okay, based on that error, what will happen? Your robot is not making that much dynamically balanced. Okay, then it is that much dynamic. Suppose I want to make it that error. I want to make it. I want to remove that error. Okay, for that purpose, we are going to attach the controller. See here, I think if people know about the control means to regulate, direct, command, and govern. See what will happen? It will regulate it, it will command it, and it will govern it. And see here, generally there are two types of control system. Generally, people they are using. If you go for any industry, one is the open loop control system. Second one is the closed loop control system. What will happen when we are going to the open loop control system? Whatever the input you are giving, suppose there is a system, you are giving the input, and what will happen based upon the input, and the system will do some calculation. Then it will give the output, but we don't know whether the output is correct or not, whether the output is reaching our target is not. Okay, whether whatever the output is coming, that output is reaching our target or not, that we don't. Okay, but that we don't require. Suppose what we need to maintain the our dynamic balance margin. How we are going to check it, whether my joint is moving from 30 to 45 or not. Suppose we are giving the input to open loop control system. If it is giving the input some value, but it is not reaching. Okay, it is reaching only 42 degrees. Then there is error, 3 degrees error is there. Okay, that we don't know how much error is coming and what is these are the things. That means it is not reaching your target. Then suppose when you go for closed loop control system, what will happen when you're providing the input and based upon the system, okay, your target is also there. Your target is 45. Then it will measure it. Okay, it will check it whether I am reaching exactly target or not. If it is not reaching exact target, what will happen? That error it will send to the again closed loop. It will send back to the closed loop by using closed loop. Then again it will try to rectify it. Our main aim is to reduce the error and stabilize the system. See, among all the controllers, PID controller is most common control algorithm used in industrial automation applications, and more than 90% of the industrial. See, there are number of controllers are there, number of control algorithms are there. People are using PA type, PD type, PID type, and sliding mode controller, observe based controller, computed torque control method. There are number of control methods are there, but still people are more focusing on the PID control. Why? Because PID controller is best control algorithm for all industrial applications. That's why people are more focusing on the PID control algorithm. And now you can see how to design a PID controller. Okay, see, when we are solving the dynamics, okay, we have calculated the torque equation. Then after calculating the torque equation, see here, this is the PID controller equation. This is the general PID control equation. Okay, this is the actual PID controller. This is the required PID. Okay, this is the required torque and this is the actual torque. Okay, this is the required torque when you are going to dynamics of the biped robot, and when you are going to calculate the PID control, this is the actual torque. See here, this is the PID control equation: Kp E of t plus Kd dE of t by dt plus Ki integration of E of t dt. If you go and open any control system textbook, you can see this type of equation easily. Then here E of t is nothing but your error. And Kp is nothing but your proportional gain. Kd is nothing but your derivative gain. Ki is nothing but your integral gain. Okay, here see EF. What is the error? Error is nothing but my final. That means I want to reach 45 minus 30. 45 minus not 30, 45 minus how much it is reaching. Okay, it is reaching 42 or 41, 43, 44. Okay, the final minus my initial angle. That is called the error. Now see the tau actual. See, when we are going to the actual torque, when we are going to calculate the Kp into the error we are calculating, the final minus initial, then we are going to keep in, we are going to substitute these error, the whatever the error is, the error equation, we are going to substitute in the original equation. Then what will happen? You now you got the actual torque equation by using PID controller. But I want to control my robot. I want to control my, I don't want to bother about the actual control equation. I want to bother about my robot control. Okay, I want to identify how much torque required for reaching that position, how much torque required to move my joint from one position to another position. Okay, for that purpose, what I need to do, I need to I need to substitute these all the equation into my original torque equation. See here, you can go back once. See, suppose I want to move these all. I am writing the in terms of angular acceleration q double dot j. I want to move all these terms to left side. See, tau I minus gi minus sigma j equal to 1 to sigma k equal to 1 to n hij q dot k, and this term it will come into by denominator. It will come. See the same thing. Sigma j equal to 1 mij q inverse. These are the minus. And wherever tau I, the tau I, whatever the tau I is there, that is the torque. There I am going to substituting this PID, original PID controller equation. Okay, see here what will happen, the integration. See here, the wherever dE of t by dt, dE of t by differentiation, we have done differentiation here. Okay, and then integration. Okay, integration of u theta I. The integration means here we are going to calculate by using the state space. By using the state space, we are going to calculate. And this is the equation, the xi dot equal to theta minus theta. And this is my final control equation. This is my final control equation. In terms of angular acceleration, I am going to calculate in terms of angular acceleration. Now see what will happen. Now I want to see here we have developed the PID controller equation in terms of angular acceleration. Now what will happen? I am going to tune my gains. Okay. Otherwise, what will happen? Now it is supplying, but my error is not reducing. How the error is reducing? You need to stabilize your system. You need to stabilize your system. How to stabilize it? You need to reduce our error. Okay, you need to play with your Kp, Kd, Ki. You need to give the proper gains. You need to supply the proper gain. Actually, see, to supply the proper gains, okay, what will happen in generally the researchers people are there using. There are different types of tuning methods. One is the manual tuning method. This manual tuning method is the trial and error process method. It is a trial and error process method. It is a laborious time and it will take the time consuming, and we cannot get the better value. We cannot expect the better value by using this manual tuning method. To see what happened, the people they have used, maybe there is another method, that is the Ziegler-Nicholas method. How this Ziegler-Nicholas method, it will work based upon some formulation. Okay, some mathematics they are going to calculate this Ziegler-Nicholas method to determine the best gains, to provide the best gains. Nowadays, actually, most of the researchers they have moved to soft computing algorithms like optimization or neural network, fuzzy logic, this type of. And also here also we have developed the optimal PID controller. We have optimized we have tuned the gains of the PID controller, that Kp, Kd, Ki, by using some optimization algorithm, some nature-inspired optimization algorithm. That's why we call it as an optimal PID controller. Then see here, coming to the optimal PID controller, here this is the closed loop control system. This is the complete closed loop control system, what you were seen earlier. And here we have used this MCIW and PSO. We have seen here, okay, MCIW and PSO. What this MCIW and PSO will do, it will try to, okay, by using manual tuning method or Ziegler-Nicholas method, we can identify the maximum and minimum to stabilize the system. Okay, but we don't exert the stabilization point, that we are going to try to identify by using this optimization algorithm. Here MCIW, that is modified quadratic inversive weed optimization, and PSO means particle swarm optimization algorithm. See what will happen here, when we are going to discuss about the optimization, we need to first identify our objective function. What type of objective function you are going to optimize it? Okay, whether it is a minimization function or whether it is a maximization function. Suppose here what will happen, I'm trying to reduce my error, I want to stabilize it, but for stabilizing I want to reduce my error. Okay, see that's what we call as my objective function is minimization of the error, and this is the my objective function. Okay, error in angular displacement for swing leg, error in angular displacement for stand leg, and these are my constraints, and this is my equation. Okay, 1 minute, please give me 1 minute break. 1 minute. Yeah. See, this is the my objective function, minimization of the total error, and these are the constraints, the KP, KD, KI. KP, KDI, one of the swing leg and stand leg. And see, I have said we have used the nature inspired optimization algorithm. I think one is the PSO. I think most of the people they know about particle swarm optimization algorithm. Maybe they have used maybe different problems also. Maybe you may also use all people. Maybe use your problems. This is the PSO algorithm, genetic algorithm, differential evolutionary algorithm. These are all the things. Okay, and I'm going to discuss about what is MCAW. Okay, I'm not going to discuss about the PSO. Why? Because you will feel bored once again to repeat this one, and I'm going to discuss about this MCAW. See how this MCAW is coming out. Okay, based upon the standard. Okay, IW, that is invasive weed optimization algorithm. See, I will give you just a brief outline how this algorithm will work. I think you all people know about the cultivation land. In the cultivation land, there are some useful plants, some unuseful plants. Okay, the useful plant like your paddy or it may be wheat or whatever it may be. Whatever the useful, okay, and the unusual plant means it is generally weeds. Okay, it is unusual plant means weed plants, but it will not provide any useful things. Okay, why it is coming? How it is growing these unusual plants, the weed plants, how it is growing based upon the what will happen to grow our crop. We are providing some fertilizers and pesticides and all the things. Okay, and what will happen, all the whatever we are providing, all the nutritions the usual plants will not take it. Some nutrition maybe leave the land. Okay, these unusual plants, that means weeds, these weeds, what will happen, it will take the whatever the extra nutritions, whatever the unusable nutritions, it will take and it will grow it. These unused the weeds will be growing, and these weeds how it will grow based upon the whatever the unused resources. Okay, see here what will happen, these grows these weeds, what will happen, it will grow it, and then again it will, what will happen, again it will do flowering. Okay, the weeds will also flower it, and again it will generate the seeds, and again that seeds will be fall down, and again it will take it unusable resources, then again it will fall. And for each plant, initial stage, each plant, how many seeds is generating? Okay, each plant is generating depends upon the fitness. Fitness means depends upon how many nutrition. Okay, how much strong the plant. Okay, how much healthily strong. Okay, based upon the healthily strong, that we call as a fitness. Okay, based upon the fitness value only. Okay, the plant will generate the seeds. Here, what will happen? This weeds will generate the weeds will be, what will happen, it will make it as a flowering plant, then again it will make it as a number of weeds, then again these weeds also make it as a flowering plant, again it will be make it as a number of weeds. Okay, after flowering, what will happen, there are number of plants are there, weed plants. What will happen, based upon the fitness value, we are going to make it the order, we are going to give the ranking system. Then how many plants are, okay, it is required to participate in our problem. Okay, we are going to participate, suppose I need the maximum plants 100 is required, we will take the best 100 and we are going trying to keep it, and we are going to provide the ranking system. And see, this is the back end concept how this algorithm is working. Okay, this algorithm was developed by Mehir Bien and Lucas in 2006. See, in the initial stage, what will happen initially, the number of feeds, okay, that is called the problem variables. Okay, here are dispersed randomly in a d-dimensional solution space. what will happen? The weeds is nothing but here in this problem, the KP, KD, KI is the my variables. KP, KD, KI. Why? Because I want to identify KP, KD, best KP, KD, KI. Okay, that is my variables are dispersed randomly in a d-dimensional space between the maximum and minimum value of individual. Okay, how much distance it is? Suppose one weed I am keeping here, second weed. How much distance is there? The maximum distance and minimum distance. That we need to calculate. The second case is that reproduction stage. Okay, here what will happen? Each weed produce the number of seeds. Okay, what will happen? It is growing and it will produce the number of seeds based upon the fitness value. How much the strong the each plant. Okay, how it will be strong? If the plant will take more number of resources, then more number of nutrition, then the plant should be very healthy. If the plant is not taking, it is not getting any unusable resources or nutrition, then the plant should be very weak. See, each weed produces the number of seeds based on the fitness value of the flowering weed in a colony. The number of seeds reproduced from each weed. Okay, the number of seeds, whatever the seeds is calculating. Okay, how many it is reproducing based upon the number of seeds. How many it is reproducing based upon the fitness value only. You can see in this figure here the x-axis is showing us the fitness value and y-axis is showing the number of seeds. Okay, x-axis is showing fitness value. See, if the more fitness is there, more number of seeds. Okay, and if less fitness is there, less. Suppose the fitness is less number of seeds. If the fitness is more number of seeds is generating. How we know how to calculate each plant, how it is generating the number of seeds? We are going to use this formula S equal to flow into S min plus F minus F minimum by F max minus F minimum into S max. Here S is nothing but number of seeds, F is nothing but fitness. Here the F max is the maximum, F minimum is the minimum, and F is nothing but the average of the fitness. Then what will happen? Here what will happen? Initially you have spread the weeds, then it is making as a flowering plant, then it is generating also again seeds. Okay. Now what will happen? We have seeds. Already plants are there. We have seeds already there. Okay. Now we are going to the second stage of seeds. We are going to spread it. Okay. How we are going to spread it? By using in the spatial dispersal concept. See, the seeds produced by each flowering weed are dispersed over the set space. Okay, that is the set space. Whatever the farming, the cultivation land, it is called set space. By using normal distributed random number. How we know where we need to distribute exactly? We don't know exactly. By using what will happen? Using normal random distributed number. Okay, based upon the normal distributed random number, we are generating. How? With mean equal to the position of the plant and with varying the standard deviation. We are going to try to varying the standard deviation based on the value of change in variance. Okay, suppose if you want to change the variance, the new seeds are distributed around the parent weed. What will happen? Sometimes whatever the seeds it is generating the weed plant, it may be sometime based upon the variance, based upon the change in variance, it may be fall down nearby the parent weed only. At the end of each generation, the standard deviation of the present problem, how we are going to calculate the standard deviation by using this formula, sigma gen equal to gen maximum, that is maximum generations minus gen by gen maximum power n. Okay, here n is the index term. Okay, n is the number of index term and sigma initial minus sigma final, and this is the standard deviation of the initial and final standard deviation. And see, now you have generated. Now finally what is we need to do? We are going to competitive exclusion. Here once the seeds have found their position, now whatever the second stage seeds, it is found their position over the set space, the seeds grow to the flowering plant and they are ranked together. Now what will happen? Already previous plants means just we consider for understanding, we can keep as a mother or father plants. Okay, now child plants came. Okay, the child plants also growing based on the unused resources. Now we can check it. Which one is the more strong? How we check it? Again, the parent will give the seeds and the child will also provide the seeds. Based upon the fitness value, okay, it will provide the seeds. Then what will happen? There are number of plants are available now based upon the fitness value. What we need to do? We need to give the ranking system. We need to give the ranking system. How we are going to give the ranking system? Which one is the maximum ranking? Maximum fitness is there. That is the rank one. And less fitness is there. Very less fitness. It will go to last rank. Okay. Then you need to segregate like that. Once the number reaches the maximum number of plants, the Pmax, the plant with lower rankings are eliminated. Suppose I need 10 solutions, I need 100 solutions. Why? Because suppose why we are generating these 10 solutions, 100 solutions. See, all these weed plants are called solutions. All these weed plants are called solutions now. Okay, whatever these solutions, suppose I need 10, 100. Our main aim is to get the global optimum solution. Our main aim is to get the global optimum solution. Suppose what will happen? Why global optimum solution we require? Suppose initial stage. Okay, initial stage, the weed plants, it is generating some seeds. Now there is a one fitness value. Now there is a, that is called local optimum solution. There is a one fitness, best fitness is there. That is local optimum solution. But extend second generation, then third generation, then fourth generation. Then we are comparing all these generations. Then which one is the best? Then that is our global optimum solution. Based upon the global optimum solution, that means we are trying to achieve our global KP KD KI. We are trying not local KP KD KI, global KP KD KI. Why? Because we are trying to stabilize our system by using this KP KD KI. We are matching. See how I am matching. I am matching with the whatever the weeds are there. That weeds is nothing but my KP KD KI. Okay, I have generated weed plants. Okay, I have segregated based upon the fitness, and that is called my KP KD KI. By KP KD KI. See what will happen? Each generation it is give one fitness, that is called local fitness. And when you're comparing with the all the generation, maybe second generation, third generation, fourth generation, then we are comparing. Okay, what will happen? Then we will get the which one is the best fitness. The first, maybe first generation one came, second generation one came. Out of four, which one is the best fitness? The best fitness will go to, that is your best KP KD KI value. Then what I have discussed up to now, the inverse weed optimization algorithm. But how it came, this modified cohetic inverse weed optimization algorithm? What I have done, I have modified. Why? Because why I have modified? I am planning to improve the performance condition should be improved. Okay, I am trying to improve the performance of the algorithm. Okay, based upon the literature review, I have taken one cohetic random map, cohetic random number. See, initially I have used here normal distributed random number. What I have used instead of normal random distributed number, if I use the cohetic random number, what will happen? Okay, in the normal distributed random number, what will happen? It will go different places, but the weed, whatever the second time we are giving or third time we are providing, it will may not take sometimes, or it may be two weeds, maybe 2 or 3 weeds maybe fall down at the same place, and these 3 weeds fighting to each other to take the unused resources. But when you're going to use this cohetic random number, it will give each and every based upon this cohetic random number. There is no chance to fall down. Okay, or 2 or 3 weeds, it may be in single place, and it will go to each and every corner of the place, and it will try to utilize the unused resources. It will try to utilize the unused resources, and it will try to fight with the maximum best fitness plan. It will try to fight with the maximum best fitness plan. Okay, for that purpose, what will happen? I have chosen here cohetic random number. This cohetic random number, what will happen? It will try to minimize the chances of solution to trap into the local optimum. Okay, what it will happen? It will try to minimize the chances into local optimum. See, when I'm going to use the cohetic random number, this cohetic random number we have obtained by using the Chebyshev map. Okay, this is the equation we have considered for generating the cohetic random number. X of k plus 1 cos of k into cos inverse of xk. And also we have done one more modification to improve the performance of the algorithm. That is the cosine term. Okay, that is the cosine term. Okay, here what will happen based upon these cosine term? See, the main aim of the cosine variable, it increase the set space. It will go to different places and it will utilize the minimum resources. What will happen here? We will go cosine term. If you are going to add this cosine term after cohetic random number, we are going to add the cosine term here. Then what will happen? This, when you are going to use the cohetic random number, it will try to push it different places, all the weeds. But when you are going to use the cosine term, what will happen? You will try to utilize the minimum resources. Whatever the minimum resources also, it will try to utilize it and will try to make the best fitness. See, we have what we see here. Earlier there is no cosine term. We have added this cosine term. Then when we have checked with the IWO standard algorithm and modified cohetic inverse weed optimization algorithm. See, the standard deviation, when the number of generations are increasing, the standard deviation, what will happen? See, it is linearly decreasing. But when you're going to use the modified cohetic invasive weed optimization algorithm, what will happen? See, it is just jiggling. Okay, it is going to do jiggling structure. What will happen? It is going to different corners and try to identify what are the resources are there and try to utilize the even the minimum resources also. This dotted line. And see, this is the flow chart, how the algorithm is working on initialization. See, whatever the I said, the weeds is nothing but KP, KD, KI, and initially it will go to the search space. And then what will happen? We will evaluate the fitness value and we'll try to identify the error. How much error is there in the angular displacement? Okay, in each stage. Then it will go to reproduction using cosine and cohetic variable. Then it will go to spatial dispersal, the third stage. Again, it will distribute. Then it will check the total number of weeds and seeds, whether it is sufficient to participate in this solution or not. If it is sufficient, we'll go for competitive exclusion. Okay. Then if it is not sufficient, again it will go and again it will participate up to how many Pmax, the maximum fitness. Okay, the maximum number of fitness weeds is required. How many it is required? Then when you're reaching up to that stage, the process will be continue. The process will be continue. And finally, you will get the best KP, KD, KI. That the global optimum solution, you will get it. Okay, then see, coming to the one more controller. See, this is the optimal PID controller. This one. Then second one is the adaptive PID controller. What we have done here, instead of giving, see, in the optimal PID control, what will happen? Whatever the input you are giving, based upon the input, it is giving the output. Suppose suddenly we are giving some new input. Okay, some new input. Okay, in the optimal PID control, what will happen? Whatever the known input we are giving, the known output is coming. But when you are going to adaptive controller, you are trying your system between suppose the angular displacement should be some 30 to 40. Okay, suppose I want to provide the input in the 42 degrees, the angular displacement. Okay, the variation in the angular displacement I have provided 42. Then based upon this magnitude, okay, based upon the 42 degrees also, it will generate the KP, KD, KI values. It will generate the KP, KD, KI. That is called adaptive. That means that is intelligent control. We call as a one more name, intelligent control. Okay, that's we are using neural network controller. Okay, nowadays actually people they are using to develop the mission intelligent algorithm. They are using, there are various types of these neural networks they are using. It may be artificial neural network, or it may be recurrent neural network, deep neural network, and there are variant. There are so many radial basis function neural network. They are using different types of neural network they are using. Okay, see. We're going to discuss about the story behind that this neural network. See how this neural network has came out. See, when you're going to discuss about the, suppose before going to the neural network, we are going to discuss about the biological neuron. Biology. See, I think you all people know about, we have a neurons in our body. We have already studied this subject maybe in our +2, or it may be ninth standard, or it may be 8th standard level. In our body, there are number of neurons are there. Based upon the neurons only, we are getting the information. Okay, the information, and we are doing some task like that, and we are taking the decision immediately. See here, what will happen? See, neuron is a special biological cell that processes information. What it will do? Suppose you have one idea, and it will process one neuron to another neuron. Then it will do finally you are doing some task. Okay, there are huge number of neurons, approximately 10 to the power of 11. 10 to the power of 11 with numerous interconnections, approximately 10 to the power of 15. See, here what will happen, this dendrite, see, this is the biological neuron structure in our body, how it is there. This is the dendrite. The dendrite, what will happen, it will take the information. It will take the information. That means that is acting as your input. Okay, it will take the information to your body. And then cell body, here what will happen, cell body is nothing but, it will, here what will happen, it will do processing. Okay, suppose you are getting some information, the dendrite will take it, then the cell body will do processing, and what we need to do immediately. Okay, then what will happen, it will process it here, then immediately it will send the whatever the output is coming, it will send to the axon. Axon is the connection between the one neuron to another. The axon is the connection between the cell body to the synapse. What the synapse will do, the synapse will be sent to this, whatever the signal we are providing, that will send to the second neuron. It will send to the second neuron. That means dendrite you act as an input, and synapse is act as a output. Synapse is act as a output. Now you can see when we are going to compare with biological neural network and artificial neural network. See, See what is artificial neural network here? Artificial neural network also, see here also there are some inputs. This we call as a dendrites, and we are connecting between the whatever the connecting between the input to the summing junction. Okay, the summing junction, and from summing junction it is connected to active function, then it is go to output. Here you consider as a, see whatever the soma. Okay, soma is nothing but your node. Okay, that is called these called your nodes. Okay, initially there is a nodes will be there connecting between this input to this input. That means here, suppose if you connected from here to here, there is a one nodes are there, that is called soma. And dendrite, these are the inputs, and synapse is the weights are interconnections. Okay, it is one layer to another layer connection, but it will send the signal from here to out. Then axon is the output. Okay, this is the your output. This is the what here it is processing, then it is coming to the output. This will go to synapse is the connecting between the next neuron, then this output will go to next neuron again. And see the similar structure we have developed the artificial neural network also. See here the information problem which works based upon the principle of biological neural system. The interest in NS come from the ability to mimic human brain, learn and respond. How our human being is responding based upon the this response they have taken, they have developed this neural network. And why this artificial neural network is required? See why it is required. Actually, as a childhood we don't know how to walk, but actually what will happen, our mother, father, then brother, sister, after the teacher, they are teaching, okay, how to walk, how to do, how to, what are the things, this is the chair, this is the pen, this is the book, these are all things. How we know? We are, they have teached us. Okay, like that now we are also teaching our kids. Okay, then only they know this is the pen, this is the book, and they otherwise they don't know what which one is the valuable, which one is the not valuable also. Okay, and see like teaching we are developing, we have our own intelligence based on the teaching we have developed. Okay, but robots don't have any own intelligence power. We need to teach it, to teach that whatever the things we are going to develop the own intelligence power, we are going to teach the robot. How we are going to teach? By using this neural network concept. See here what will happen, with the help of neural network we can find the solution of such problems for which algorithm method is expensive. See generally what will happen, suppose whatever the solution, where some problems you can take it by solving algorithm method, it is very difficult, that type of problems. When you are going to use neural network, that type of problems can be very easy when compared with the algorithm method. That type of problems we can solve it, and neural network can learn by example. Hence we do not need to a program at much extent. See nowadays actually there is a graphical user interface method is also available, no need to write the programming level everything. Okay, you can, there is a graphical user interface method is also sufficient. And neural network have the accuracy and significantly fast speed than conventional speed. Okay, it will provide the accuracy, and it will also provide the significantly fast speed than conventional method. Okay, when you are going to compare with the conventional method, this neural network will provide better accuracy, and also it will provide the fast speed. Then coming to the, see, when you are going to discuss about this neural network, see there are various types of activation functions we are going to use. One is the linear activation function, second one is the log sigmoid activation function, third one is the ton sigmoid activation function. See here, see the linear activation function y equal to a into u, and the log sigmoid 1 by 1 plus e power minus au, tan sigmoid e power au minus, that is not x, that is u, e power au minus e power minus au by e power au plus minus e power minus au. See what will happen when we are going to discuss about this neural network. There are number of layers and number of layers. Okay, number of layers of the neurons are there. Okay, where we are going to use this activation functions. Okay, we need to use the first layer or hidden layer, or it may be output layer, which type of layer we are going to use. But when you are going to process the information from one layer to another, we need to use some activation function. Based upon the activation function, the activation function, what will it will do some calculation, then it will send the data to next layer, then from there to next layer, like that it will do it. And see here how the multi-layer feed-forward neural network will be there. See, this is the input layer. See, I have written here input layer, and this is hidden layer, and this is the output layer. The input layer connecting between the input layer and hidden layer. there is a some weights. Okay, there is a some weight that we call as V11, V12. That is the weights between the input layer to hidden layer. And see, these are the nodes. These are the nodes. This is one node. This is one node. This is one node, like that. Then the weights is connecting between the hidden layer to output layer. That is called the another weights. Okay, that is called hidden layer to output layer weights. Okay, and also see here, the input layer, we are providing the input, and after doing some activation function, after applying some activation function in this layer, then what we are giving the some output from the input layer. This output layer, again, it will connecting with the weights. Okay, whatever the output input of the output is coming, it will connecting, it will do some, okay, some calculation, then it will go to the input of the hidden layer. See, but all the cases I have written BI, BH, BO. What is this BI, BH, BO? The BI is nothing but bias of the input and bias of the hidden layer, bias of the output. Why we need to add the bias? Okay, what is the importance of the bias? See, what will happen when we are going to do these calculation by using some activation function? Sometimes what will happen, whatever the output you are getting, suppose you are doing some activation function, the output you are getting, it may be sometimes, okay, sometimes what will happen, you will get the null value. You will get the null value. That means zero value you will get. To avoid that null value, the zero value, we are going to provide some bias value. That bias value will you to just try to avoid the null value. It will help to try to avoid the null value. Then see, and one more thing, you may have doubt where we need to use this activation function. Whether I use the linear function in the input layer, whether I use the log sigmoid function in the hidden layer, whether I need to use the tan sigmoid in the output layer. No, that is we cannot take randomly like that. We need to do some parametric study. If see, my input is this one and my output is this one. Okay, which output is this? Suppose I got YO1, YOK, and YOP. Based on these output, whether I'm my whatever, suppose I am going to make the dynamic balance margin, whether I am going to make my control system, okay, my gains, okay, that my target is that my final target is that I want to make them more dynamically balanced. Okay, by taking these gains, by these things, whether I am getting more dynamically balanced or not, first I need to check that. Okay, see, like that we need to check it. We need to do some parametric studies. First I will keep linear function here, log sigmoid and tan sigmoid. Then we'll do some trial and error method. We need to do some parametric study. Okay, parametric study we'll do it. Then next we'll change it. Log sigmoid here, linear, tan sigmoid, like that. Then in which condition we are getting the better dynamic balance margin? That depends upon your problem. If I am discussing about your dynamic balance margin problem, that depends upon your problem. Sometimes maybe you are going to use image processing. Okay, where it is getting the exact information, where you are getting the clarity, or maybe your exact input data, your output data you are getting by using the image processing. That depends. You need to do some parametric study. Okay, when see here, these are the formulas. You need to some mathematics. You need to for getting the output of the input, and for getting the input of the hidden layer, output of the hidden layer, and input of the output layer, output of the output layer. These are the formula we have used. And then see, I'm going to discuss about this optimal PID controller. See, now see what will happen. I already discussed it. The optimal PID controller will use only one set of optimal values. Okay, that's why we have used this neural network controller, adaptive controller. See, the adaptive controller, it will generate the variable gain based upon the magnitude of the error. Suppose the error is increases suddenly. Okay, what will happen? Based upon the error, the gains values will be changed in the adaptive controller. But in the optimal PID controller, it cannot possible like that. It cannot possible like that. The adaptive PID controller will works with the help of neural network structure. Further, the weights of the NN. Okay, here what will happen? Whatever the weights, the V11, W11, the weights between the input layer to hidden layer, the weights between the hidden layer to output layer, we are going to again optimize that one. For to optimize these weights, okay, whatever the weights between input layer to hidden layer to output layer, again we are going to use some optimization algorithm, non-traditional optimization algorithm. That again we have used the same optimization algorithm, the modified quadratic inverse speed optimization, and again the particle swarm optimization algorithm we have used, and we have checked which algorithm is performing better. Okay, see here, this is the that flow chart. Okay, the flow chart here, it is showing, okay, how the algorithm is works. Okay, these are the input we are providing. The input is nothing but we are providing the angular displacement. This is called angular delta theta 1 minus delta theta 1 equal to what is the final minus initial angle. Okay, angular displacement we are providing as the input based upon the angular displacement. That means based upon the error, how much difference is there. The angular, if you are your target is 45, now your it is reaching 42. What is the 45 minus 42? What is the error is? The 3 we are giving the input. Okay, that we are providing the angular displacement. We are providing the 3 based upon the error. We are getting the Kp, Kd, Ki value. Why? Because we are going to try to make the stabilize the system. We are trying to reduce our error. We are trying to reduce error. Okay, the further process we want to tune your Kp, Kd, Ki. And here to reduce to calculate that error, okay, how much error you are getting, that to reduce that error we are going to check with the root mean square deviation. We are using this formula. And see here, D is the number of training scenarios, how many trainings you have done. You have done 100 training scenario or 1000 training scenario. And B is nothing but number of intervals. Okay, how many intervals you are going to give it to reach one position, from one position to another position. And P is the number of joints. P is the number of joints. And see, when we are going to see up to now what we have discussed about the only how to generate the guide generation and how to design a PID controller and how to tune the gains of the PID controller. Okay, these 3 things we have discussed. And now what will happen? I am going to show some results. Okay, when we are going to tune the system by using optimal PID controller, and when you have tuned the system by using neural network PID controller, and also I can show you some manual PID controller also. See, this is the we have done before actually. Like I think maybe you people know how GA and PSO, they have some own variables. Okay, like this modified cohetic inversive weed optimization also, they have some own variables. Initially, we need to identify the best value of each own variable of the algorithm. Okay, here the own variables, standard deviation, exponent value, the maximum number of seeds, okay, and maximum population, maximum number of generation. For that purpose, what we have done initially, we have conducted a parametric study for modified cohetic inversive weed optimization algorithm when we are using the optimal PID controller, and PSO parametric study for PSO also. Then what will happen when we are going to use the neural network adaptive controller? Here what will happen? Your neural network is generating your KP, KDK, but what MCAW is doing to tune the weights of the neural network, And here also we have done the parametric study of the MCAW and again the neural network. See, I have told generally we don't know how many number of hidden neurons. No one has given the number of hidden neurons, how many we need to keep it. That also we need to do the parametric study. Okay, we know the input and we know the output, but how many we need to take the number of hidden neurons, that we need to take the parametric study. Okay, once we done the parametric study, then only we can get the conclusion. Okay, these many hidden neurons is providing the best KP, KD, KI or best result it is providing. Then now you can see this tabular column, you can identify the manual tuning. When I'm tuning with the manual method, what is my KP, KD, different joints. And when I'm tuning with the modified cohetic inversive weed optimization, that is optimal PID controller, and PSO, that is also optimal PID controller. And when we are going to use MCAWNN and PSONN, okay, you can see when you're using neural network controller, that is adaptive PID controller, what is KP, KD, KI. Okay, see, only this manual only in our hand we are controlling, but the remaining things, the algorithm, we are giving the only maximum minimum value, the best value the algorithm will generate. The algorithm will generate the best value based upon the whatever the process, how the algorithm is working. Based upon the algorithm, I said the weights is nothing but my KP, KD, KI. Okay, how the algorithm based on that it will perform, it will give the best result. Then what will happen here? I am going to present some of the results. Initially, we have calculated the error at different giants. Okay, we have shown some of the giants. See how the error is stabilizing. How the error, the manual error and MCAW when you're using PSO, when you're using MCAW and MPSO and okay, how the error is stabilizing. And we have also concentrated on the torque required. Okay, the variation of the torque required at each joint of the biped robot. And see here, you can observe we have presented some of the joints. Okay, when you are seeing here, there is a black color indicates manual, red indicates MCAW, the blue color indicates PSO, green indicates MCAWNN, the purple indicates PSONN. Okay, see here what will happen here. There are 5 algorithms I have given. You can see giant 2. Which one is the taking? See, when you are going to discuss about the torque, which actuator is taking less torque and when the reaching our goal. Okay, to reach our goal. Okay, less torque is required. Okay, see, when you are observing this figure, all of you please see here the green color, the MCAWNN controller is taking less torque required to achieve the our position. Okay, then see, this is the C in each joint 2, joint 3, joint 4, every joint. Then we conclude that this algorithm is performing better than other algorithms. And similarly, now we are going to calculate the zero moment point. Where the zero moment, see, the complete, this C, you can see the complete from here to here. Okay, this is called my robot is walking on 4 steps. Okay, and this I am indicating enlarging view. This is called my 1 foot. From here to here, it is called 1 foot. Here, see, suppose if you consider as the center of this foot here, initially my ZMP is here, then slowly it is moving forward direction. See, when you're using manual tuning, MCAWO, PSO, MCAWN and PSON, you can see MCAWN and C here. When you compare with the C, MC manual, then you can see MCAWO, then PSO, then PSONN, then C, you can see here, this is the MCAWO. That means your ZMP is nearer to the center of the port. See, always your ZMP is nearer to the center of the port. Okay, for each and every condition, your ZMP is nearer to the center of the port, then your robot is more dynamically balanced. Okay, if your ZMP is away from the center of the port, away means it is far away from the center of the port, then your robot is going to be less dynamically balanced. That we need to keep in mind. And after done, so after completion of the simulation, we have done the real time. Okay, the experimental work we have done real time, and we have observed whether the robot is working in the same way or whether the robot is balancing, dynamically balanced, or it may be fall down. We have observed, and this is the flat surface, and this is the done when the robot is walking on the ascending the staircase, and this when the robot is walking on the descending the staircase, and this is the when the robot is working on the sloping surface, when the robot is ascending the sloping surface, and these are the results when the robot is working on the descending the sloping surface. I will show you some videos also related to how the robot is walking. This is the snapshots when I to keep in my research papers. I have cut it like this. I will show you the some videos related to how the robot is working also later. Then when you're going to see the overall comparative study, when you're discussing about the overall comparative study, see, our main aim is to, from starting onwards, I am talking about only to increase my dynamic balance margin, more dynamically balanced margin. When you're using manual tuning method, when you're using optimal PID controller, when I am going to use adaptive PID controller. See, here I am giving the x-axis, the terrain, various terrains. I have tested flat surface, I have tested ascending the staircase, I have tested descending the staircase, I have tested slope ascending, slope descending. And in the y-axis, I am giving the dynamic balance margin in x direction. Similarly, I have given the y direction. X means this is the sagittal plane, and y means this is the lateral plane. Don't confuse it. This is the lateral plane, this is the sagittal plane. Sagittal plane means this is the side view, this is the front view. See what will happen. You first try to understand. See, you can see the blue color, the green color indicates MCAW. For all the terrain conditions, see all the terrain conditions when you are using MCAWNN. Okay, controller is providing more dynamically balanced margin than compared with the other 3. Okay, sorry, other 4. See, this will be top. That means your dynamic balance margin more than other, okay, other controllers. Okay, other controllers. Okay, then see one more thing you can see here. See, when the robot is working on the flat surface, is one more condition you can observe. First is the MCAW in performing the better, and the second one is the your robot is working on the flat surface is more dynamically balanced. See all the terrain conditions, sorry, all the controllers. When you're going to use all the controllers, when the robot is working on the flat surface, it is more dynamically balanced than stair, than sloping surface. Why? Because we see, as a human being, we are also working on the flat surface. We are more dynamically balanced than when we are working on the stairs, than we are working on the slope surface. Okay, the same similar structure we got the here also. That means we are also, this is the natural behavior of the human being. That means we are already when we are going to compare with the natural human being, the result will also it is coinciding. And similarly here also the dynamic balance margin in y direction, you can see the MCAWNN is performing better than other controllers. Then when you're coming to the torque we have shown here, the torque required less in when you're using the modified quadratic inverse speed optimization with neural network, that is called adaptive PID controller. Then when you're going to calculate after we have evaluated the torque, and we need to calculate the power, how much power consuming for each to reach from one position to another position. Okay, for each joint. Okay, when each terrain condition. Okay, you can see here when what is our aim? Our aim is to less power and more work. Our aim is the less power and more work. Less power and more work. See what will happen when you're going to compare it here. What will happen? This is the terrain conditions in x-axis and the average power in y direction. See what will happen in the all the conditions, all the terrain conditions. See, when we are using modified quadratic inverse video optimization algorithm with neural network, when compared with the PSO, this is also PSO is also adaptive, and this is also modified quadratic. It is providing best result. That means less power consuming. It is consuming less power than compared with the other controller. Because the reason is that the modified quadratic inverse video optimization will work based upon the quadratic random number and the cosine term. Okay, it will try to identify the adaptive. Okay, sorry, it will try to identify the global optimum solution then compared with the local optimum solution. And see, you can see these are the some of the simulation results. Sorry, experimental results when the robot is walking on the different surfaces. How the robot is walking on flat surface, how the robot is walking on the ascending sloping surface, descending sloping surface, stair ascending, descending cases. And these are the publications related to completely biped robot. If anyone want to interest to work in this area to related to guide generation, related to dynamic balance margin, related to any controller, if you want to work any optimization algorithms or neural network, you can see my papers and you can get some information. If anyone want to any doubt, these are the book chapters. And these are the conferences published related to biped robot. And this is my email IDs. One is my personal, second one is my official. Then this is my WhatsApp number. You can contact if you have any doubt, if you are really working on this area. Okay, and I'm stopping up here. Thank you for your patience. Actually, it is a 2 hours talk. I have completed maybe I think around 10 minutes before. Thank you for your patience. If any doubts from your side, if you want to ask any questions, please try to ask. Now it is open. Otherwise, you can post in chat box also. You can post in chat box also. I can see.
Thank you, sir. Thank you so much for your such a wonderful and informative session. Any participants who are having any doubt or query, you can ask.
You can post better in chat box. I can read and I can immediately try to explain.
So, Ravi Kumar Mandal, sir, you're having.
Thank you. Unfortunately, I am muted. That's fine. Thank you. Okay, if you don't have any questions, later also if you have any questions, you can try to contact me through my, I'll keep my contact details. You can contact at any time, no problem. If you are really interested to work. Okay.
Yes, yes.
Okay, thank you. Thank you.
For having this session for us and sparing your precious time. Thank you, sir. Thank you so much.
Yeah, can I leave or anything? I need to wait. Yes, can I leave? Dr. Yadav,
Yes, sir. Yes, sir.
can I leave?
Yes. Yes, sir.
Okay, thank you, thank you, thank you.
Okay, thank you, sir. Okay, participants. So at 3:10 p.m. we are having valedictory ceremony. So I hope you will join. Then we will have uh, a test session immediately after the ceremony. Okay then. Then we will meet again at 3:10. Thank you.